Hello Year 11, it's Miss Bailey here. For your Do Now today, please consider the following reaction, where the forwards reaction is exothermic and the reverse reaction is endothermic. And using Le Chatelier's principle, what conditions, thinking about both temperature and pressure here, would give a high yield for this reaction. So pause the video whilst you have a go at this. So with pressure, a high pressure would increase the yield of ammonia, and that is because we have fewer moles of gas on our right-hand side compared to the left-hand side. And so a high pressure would cause our equilibrium to shift to favour the forwards reaction, because it produces fewer moles. And therefore, if our forwards reaction is being favoured, we're increasing our amount of ammonia, and therefore our yield of ammonia is going to increase. With temperature, we would need a low temperature to increase the yield of ammonia, because at a low temperature, our equilibrium will shift to favour our exothermic reaction, as that in turn will increase our temperature. And so our forwards reaction is exothermic, and therefore having that low temperature will increase the yield of ammonia, because we need that increase in temperature to oppose that change. So what we're looking at today is something called the Haber process. So sometimes you'll hear this pronounced the Haber process, but British pronunciation is Haber process. So the Haber process is a way in which we make ammonia on an industrial scale. So when we looked at reversible reactions, we looked at how ammonium chloride could be thermally decomposed in order to form ammonia gas and hydrogen chloride gas. So that's on a lab scale. But on an industrial scale, trying to make ammonia, we instead use nitrogen and hydrogen, reacting them in that reaction you were just looking at in your starter. So this graph here is illustrating that yield, so percentage yield here, at different pressures and different temperatures. So our higher yield is obviously towards that 100 end, and we can see that we get a higher yield at a lower temperature. And we also get that higher yield, so if we follow our chart upwards, as we increase our pressure. So lower temperature and higher pressure is the favourable conditions for the yield of our ammonia reaction. But if we consider each of those conditions a bit more closely, so having a high pressure is going to be very expensive, because the equipment we need in order to maintain that high pressure needs to be very strong. And so instead 200 atmospheres is used as a compromise. So if we return to that graph, we can see here is the results for our 200 atmosphere pressure. And then with our temperature, where we've looked at rates of reaction before, we know that low temperatures means a slow rate of reaction. And to go with the old expression, time means money. If a reaction is happening too slowly, that's going to cost industry a lot of money. So instead, they use a compromise temperature of 450 degrees Celsius. So returning to that graph, we would see our 450 to be in this region here. So looking at our graph here, it would be around the 25% as a yield. But we also use a catalyst in this reaction, because using a catalyst is going to increase both the forwards and reverse reactions equally, because it provides that alternative pathway which lowers our activation energy of both our forwards and our backwards reactions. And so both rates of reactions are equally favoured by our ion catalyst, but this enables us to reach our point of equilibrium faster. So your task now is to explain why those optimum conditions are used for this reaction. So considering what we've just been talking about, if you can pause the video whilst you have a go at this. So optimum conditions, this means the best conditions possible. Okay, so considering why this process is so important to us. So you can see in the background here, I've got a field of crops growing. Now, plants need nitrogen to grow, but the nitrogen gas that we have in our air is insoluble in water. And so plants need to get nitrogen in an alternative way. So the way they do that is they take up soluble nitrates from the soil. But when we harvest our plants, we don't return that nitrogen to the soil because we instead keep that nitrogen. So instead, what farmers can do is they will put out fertiliser. An example of that fertiliser is ammonium nitrate, so containing those insoluble nitrates that soil needs. And ammonia is a key ingredient in making nitrogen-based fertilisers to replenish the soil. And this is what we're going to be focusing more on next lesson. If you can just pause the video whilst you make a note of this. Okay, so we're now going to consider the 5 steps in which we can produce ammonia from the nitrogen and hydrogen gas. So our first step is combining our reactants together. So our hydrogen we can obtain from natural gas by reacting this with steam. Now this requires a very high temperature and also a reminder that natural gas is a fossil fuel. Nitrogen, however, we can obtain this from air. But in order to do this, we need to cool our air down to -200 degrees, and that requires high pressure pumps in order to do this, so that we can then obtain the nitrogen through fractional distillation. We then mix these gases together and put them into a compressor where we obtain that high pressure of 200 atmospheres and the high temperature of 450 degrees Celsius. And then the next part is passing those gases over the ion catalyst beds in order to speed up our rate of reaction and the rate at which our equilibrium is reached. We are then able to obtain our ammonia by cooling the gaseous mixture, our equilibrium mixture of nitrogen, hydrogen, and ammonia. And because ammonia has a lower boiling point than nitrogen and hydrogen, we can cool it down to the point at which ammonia becomes a liquid and thus can be removed from that cooling tank. So as we looked at earlier with our graph, we do end up with quite a low yield. So realistically only 10 to 20% as the percentage yield of ammonia. But what we can do, as you can see in the diagram, is recycle any unreacted hydrogen and nitrogen back into the reaction vessel so that we don't get any waste from this reaction. So your final activity for this lesson is to complete the worksheet that's attached on the Padlet and ensure that you annotate the diagram with the 5 steps that we have just been discussing. Thank you all for watching and see you next time.